welcome to the study guide for the midterm of Physics 135A. My name is Professor Jordan Hansen, and I'll guide you through the solutions to the problems on the study guide. Let's begin with Unit 0, and the memory bank equations will come up within the context of each problem, and I'll try to reference back to the memory bank. Nerve fibers are often observed to make signals propagate at a speed of 100 meters per second. Estimate the reaction time of a person if they touch something hot. That is, the signal must travel from their finger touching a hot surface to the spinal cord and back to the finger to make it move. So I estimate the length of someone's arm, to the fingertip to the spinal cord to be about 3/4 of a meter. Now twice that distance will be the round trip distance, or 1.5 meters. Using the definition of velocity, we have d divided by t, or delta x divided by delta time. So it's a time duration and a displacement. And so we're being asked to solve for delta t. So that's going to be delta x divided by v. And so that's 1.5 meters divided by 100 meters per second. And the units will come out in seconds. So 1.5 divided by 100 is 0.015 seconds, but let's multiply that by 1,000 to get delta t in the units of milliseconds. So 1, 2, 3, that's 15 milliseconds. Now remember, this is an estimate which is very quick. So the nerve speed could vary, and most people's reaction time is a little bit slower than this. It's a time that's longer than 15 milliseconds. So let's move forward with the next problem that involved the definition of velocity. So on page 2, we have some unit conversions to practice. The speed of sound is measured to be 342 meters per second. What is this measurement in kilometers per hour? Let's start here on the left-hand side. That's 342 meters per second. Now we'd like to convert to kilometers per hour, so we need to eliminate meters. We have 1,000 meters, and that's equal to 1 kilometer. We'd like to eliminate seconds, but seconds is in the denominator, so we're going to say 3,600 seconds in 1 hour. Multiplying by these things in parentheses is like multiplying by 1 and then 1 again. But in the process, we're going to get these factors like 1 over 1,000 and 3,600. And the units will cancel accordingly. And so 342 is simply multiplied by 3.6. And that will come out in kilometers per hour. So let's get the 342 times 3.6, 1,231. So let's just say that's 1,231 kilometers per hour. Now, the next problem is very similar, but it goes the other way. We're converting from kilometers per hour to meters per second. So this will be for part B. We need to convert 5,400 kilometers per hour into meters per second. And so we want to eliminate kilometers. So 1 kilometer needs to go in the bottom, and that's 1,000 meters. And then we want to eliminate 1 hour, and that's 3,600 seconds. So the kilometers cancel each other, the hours cancel each other. We're left with meters per second, but we have to divide by 3.6. So 5,400 divided by 3.6 will be the answer in meters per second. So 5,400 divided by 3.6. Turns out that's 1,500. 1,500 meters per second. Now, a 2-liter bottle of water has a volume of 2,000 cubic centimeters, or cc's. What is this volume in meters cubed? And the hint is telling you not just to divide by 100, because we have to divide by the right factor that converts centimeters cubed to meters cubed. So let's start with the original volume of 2,000 centimeters cubed, and then how would we change a centimeter into a meter? Well, we need 100 centimeters in the bottom, and that's equal to 1 meter in the top. And the trick here is just to cube it. And so you'll have centimeters cubed in the bottom and centimeters cubed in the top. And now 2,000 is divided by 100 3 times. And so that will leave meters cubed as the final units. So 2,000 divided by 100 times 100 times 100. So these powers of 10 will cancel and you get 20. Here's another power of 10. Changes that 100 into a 10. And you get 2 divided by 100 divided by 10. So that's actually 2 divided by 1,000. And that's in meters cubed. So if we got something that's like comparable to a meter cubed, let's say we got 2 meters cubed, if you look at the size of a 2-liter bottle and then think about a meter stick and then another meter stick delineating a cube that's 1 meter on a side, that would be 1 cubic meter. So a 2-liter bottle should be much smaller than that. And if your answer comes out to be something that's not reasonable, think visually like that. So the unit 1 is vectors, and I'm going to use the special triangles because our angles are 60 degrees and 45 degrees, and as you'll see, 225 is a version of a 45-degree triangle. It's just in a different area of the graph. So let's start with part A. We're going to convert the vector x1, which has a magnitude of 5 and makes an angle of 60 degrees with respect to the x-axis, into its component form. Now, if we're dealing with a vector that makes an angle of 60 degrees with respect to the x-axis, this is a half 1 root 3 over 2. And so if in fact the magnitude of the vector is 5 kilometers and not 1, we just multiply everything by 5 kilometers. And so it will scale. So instead of that triangle, we'll have a triangle that looks like this. Here's 60 degrees, right angle. It's 5 kilometers times 1, and then 5 kilometers times square root of 3 over 2. And then 5 kilometers times 1/2. And so the y component, which we would have gotten from the sine of 60 degrees, the y component will be the square root of 3 times 5 over 2, and the x component is 5 divided by 2. So thinking like that, it's faster to just write 5 halves I plus 5 root 3 over 2j, and those units are in kilometers. B, so x2 is a vector with magnitude of 3 kilometers that makes an angle of negative 45 degrees with respect to the x-axis. Draw it so it points like this. This is here 3 kilometers here. Here's 45 degrees, so the y component will be negative. So that was x1. This is x2. We're looking for the x component. It's got a magnitude of 3 kilometers, but that will be 3 divided by the square root of 2I, because that would be the cosine of 45 degrees times the magnitude. Will give you the x component. And then the y component will be negative 3 kilometers times the sine of 45 degrees, which is 1 over the square root of 2. And we know that it's negative because this is a negative 45 degrees, so the y component points down. The units are again in kilometers. If you're not following that rationale, then let's go back up to the vector section of the memory bank. The formulas we're using are right here, these two. That's the magnitude times the cosine of the angle. That gives you the x component. Here's the x component of this vector x. The sine of the angle times the magnitude gives you the y component. Here's the y component of the vector x. And so you can combine those formulas together to use to obtain the vectors in their component form. We've done parts A and B. How about part C? So x3 is a vector that has a magnitude of 3 kilometers and makes an angle of 225 degrees with respect to the x-axis. If this is x and that's y, this angle is right here. This is 225 degrees. It's 180 plus 45. So this angle right here is 45 degrees. So we'll just keep in mind that both the x component and the y component will be negative because we're going to the left and then down. But the rules about 45 degree right triangles still apply. So we'll have x3. x3 is a vector that has a magnitude of 3 kilometers. So we'll say 3 over the square root of 2. But keep in mind that's negative I minus 3 over square root of 2j, and those units are in kilometers. So before working this longer problem, we'll take a break here and return shortly. Welcome back. So we're going to complete the vector section, and this begins with a ship sailing from harbor, and then this takes place in a two-dimensional coordinate system. So we'll say this is east, this is north, that makes this west and south. Now, the ship at first sails west by 30 kilometers, so we'll give this a vector here like that. Then it turns 45 degrees to the north and sails another 30. And then it sails another 20 kilometers to the west like this. So there's a couple of questions. First is just to draw the situation. And then B, what is the final position of the ship? So we're going to have to add vector number 1, vector number 2, and vector number 3 together to get the path uh, of the ship. So vector number 1 is just negative 30 kilometers in the horizontal direction. Vector number 2, since it's a 45 degree, 90 degree right triangle, the x component, while negative, is easily obtained. That's 30 over the square root of 2 in the I direction, and it's negative, and then positive 30 kilometers over the square root of 2 in the vertical direction. And the units once again are in kilometers. And then V3, we have another negative 20 kilometers to the west. So negative I is the westerly direction. So the key here is that all the i's add together and all the j's add together. So the final vector position will be, let's add up all the i's. So we have negative 30, negative 20, that makes negative 50, and we have another negative 30 over root 2. So what we can do is say negative 50 plus 30 over the square root of 2 I, and those will be in kilometers. And then the only j was when we took the northerly turn by 45 degrees. So that's plus 30 divided by the square root of 2j, and those units are in kilometers. You could write the final position, for example, like 50 plus 30 over the square root of 2, comma, and then 30 over the square root of 2. Those could be the coordinates um, in this notation where you have the x component, comma, y component. It's perfectly acceptable also to write the vector like that. The final question, part C, is how far is it from the origin? So what's the distance between this point and the origin? To do that, use Pythagorean theorem, and I get about 74 kilometers. Let's re-verify that. So if we take the square root of, and then it'll be each component squared, so let's plan that out like this. And then we'll go back and put in, it's 50 divided by, or 50 plus 30 divided by the square root of 2. And then over here, we have 30 divided by the square root of 2, and that all comes out to be about, yeah, 74 kilometers. So um, it should be something longer than 50 and 30, you know, because those things are being combined, but there's some amount of distance to the north. So um, all right, so that's the vector problem. We'll now move on to the motion in a straight line. The position of a particle moving along the x-axis is given by x of t, that's a function, is equal to 4 meters minus 2 times t in seconds. At what time is the particle at x equals 0? So what we need to find is when x is equal to 0. This is part A. So if I set x equals 0, then x is equal to 4 minus 2t. So 4 minus 2t, and I think t should be 2 seconds. If t is 2 seconds, then you'll get 4 minus 2 times 2, and you can solve for that algebraically. And then that will be when the position is 0 meters. B, what is the displacement of the particle between 3 and 6 seconds? So I think what we mean is x final minus x initial, but that's going to be x of 6 minus x of 3, because 6 is the later time and 3 is the earlier time. And so what we'll get is 4 minus 2 times 6 minus 4 minus 2 times 3. Let's distribute the minus signs. That's minus 4 plus 6. So that there's a 4 and a negative 4. Those will cancel each other. And our displacement will be negative 12 plus 6. So that's negative 6 meters, like that. Let's draw a graph of x of t. So this is part C. Here's x versus t. Let's say 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Now at t equals 0, that means that x is 4. If I stick t, if I put 0 for t there, then x is 4. So it's, how about 2, 4, maybe like that. And then let's say time of 1, 2, 3, 4. So if t is equal to 2 seconds, that's when the displacement is 0. So we'll put a mark there. And we know it's a line. This is a linear function. And so we just go like this. And so if you have 1, 2, 3, 4, 6 seconds, so there's some negative position over here minus the position at 3 seconds, that's going to be a negative number. Um, the question next is, what is the velocity? Well, the velocity is actually 2. It's the slope. Velocity is the slope of position versus time, and so if we're varying time and then the dependent variable is position, if the equation is linear, then the slope of that equation will be the constant velocity. So in this case, the velocity is minus 2 meters per second. One more, and then we'll take a cut. So same kind of problem, but now we're accelerating. So um, a particle is moving along the x-axis according to some quadratic formula. So what is the average velocity between two times? This was adapted from a problem we did in class. So the average velocity will be x final minus x initial divided by t final minus t initial, or just delta x divided by delta t. But in particular, I write it this way because we want x final to be expressed as the value of x at 3 seconds minus the value x at 2 seconds for x initial, and then t final minus t initial is 3 minus 2, or just 1. The units will be meters per second. Now we're going to have to use the formula to determine what is x of 3 and x of 2. So x of 3, well, that's 10 times 3, we're up to 30, minus 2 times 3 squared. Now 3 squared is 9, so 2 times that is 18. So 30 minus 18 is 12 meters. What is the value of x at t equals 2? Well, 10 times 2 is 20, minus 8 is also 12 meters divided by 1 second. And so the actual average velocity is 0 meters per second. So that's the average velocity between t equals 2 and t equals 3 seconds. If we could draw a graph, it would look something like this. We start, if t equals 0, then our position is 0. You can see that from the formula. If t equals 0, then we get 0 for x. And we go up and then down like that. Here's t equals 2 and 3. If you calculate the slope there, you'll get a flat line, or 0. But you can tell over here the velocity is positive. Let's say we cross the time axis here like this. The slope or velocity between here and here is a negative number, and so the system goes from positive velocity to about 0 velocity and then negative velocity. So clearly the acceleration, has to be less than 0 because velocity is changing and it's going from positive to 0 to negative. All right, so let's take a break and we'll return shortly. Welcome back to the study guide. So we're in Unit 2 still. A particle has a constant acceleration of 6 meters per second squared. And we're going to be asked about uh, at what time is its displacement 5 meters, and we're given the initial velocity. So all that together suggests that we could use uh, a function like this to describe its motion, 1/2 at squared plus v initial times time plus its initial position. Now, we're told it specifically has a constant acceleration. We'll call that a, and so this is the quadratic formula. Let's subtract y initial from both sides so that we get delta y is equal to 1/2 at squared plus vi times time. So y minus y initial will be delta y. Now we're being asked at what time is its displacement 5 meters, so let's rearrange even further. We'll get 1/2 at squared plus vit and then minus delta y. Let's fill in the formula now with the actual data of the problem. So we have 1/2, what's the acceleration? 6. T squared is a variable, then plus VI is 2t, and then we're looking for minus 5 meters for the displacement. So we have 0, and then 6 over 2 is 3t squared plus 2t minus 5. So once we've built that formula that describes the motion at the with the specific displacement in which we're interested, we can use the quadratic formula to solve for the time when the displacement is 5 meters. Using the quadratic formula, we'll take negative, checking my notes here, -2 plus or minus the square root of b squared. Well, that'll be 2 times 2, so 4, minus 4, and then a is 3 uh, times c, which is -5, so that's -5 all over 2a, which is 6. So the time, we don't want the time to be negative. If we take the lower branch of the solution to this problem, then that would suggest that the particle has a displacement of 5 meters at some negative time. And I think we're looking for the time in the future. So t will be -2 seconds plus or minus, but we're going to get rid of the minus and just say plus. We want some positive time. And then square root of 4 plus, what's 4 times 3 is 12, times 5 is 60. Taking the square root of that, and then dividing the whole thing by 6. So the what's in the square root here is 64. The square root of that is 8. Minus 2 is 6. Divided by 6, we have t equals 1 second. So after 1 second, the system has traveled 5 meters. Now B, the question is, what is the velocity at that time? We can use a formula from the kinematic memory bank. The v final is equal to the v initial plus the acceleration times the time. Now the initial velocity is given as 2 meters per second. We know the acceleration is 6. That's also given. We've just found that t is equal to 1 second, so v final is equal to 2 plus 6 times 1 second, and that's 8 meters per second. A football player collides with another player while running at a velocity of 7.5 meters per second and comes to a full stop after 0.35 meters. What is his acceleration? The trick to this problem is that we are at no point told anything about time, so we're going to use the formula that does not involve time. We're being asked to solve for the acceleration, and we're told that the initial velocity is 7.5 meters per second, while the final velocity is 0. That's what it means when someone comes to a full stop. That means that the final velocity is 0. So the acceleration will be negative vi squared over 2 delta x. We're given vi, that's negative 7.5 squared divided by 2 times 0.350 for the meters over which this takes place. So the acceleration, we can open the calculator to find 7.5 squared divided by 2 divided by 0.35. And it's something like 80 meters per second squared. That's very large. It's really negative 80 meters per second squared. That's 8 Gs. That's a little bit more than 8 times our weight if we use that G to convert our mass to a weight. So that's very large, and it's in this territory we wonder about concussions. So how long does this collision last? And that's the key. If it doesn't last very long, if everything is compressed into one tiny moment, then you get high acceleration. if the length of the collision is spread out over time, then the forces are not as high. How long does a collision last? Well, let's use the definition of acceleration. So A is equal to delta V divided by delta T. We're being asked to solve for time. So delta T is equal to delta V divided by A, in the same, just like any other ratio or definition of velocity, for example. Delta T then, that's negative 7.5 meters per second. That's the delta V, because we begin with 7.5 and we drop to 0, so that's a negative change in velocity. And we're dividing by 80 meters per second squared, so meters will cancel, 1 power of seconds will cancel, and the final units will be seconds. So delta T is equal to about, by the way, the acceleration is negative as well, so the two minus signs will cancel, and the delta T is about 94 milliseconds, like that. Just shy of a tenth of a second. So unit 3 takes us into multiple dimensions. In this case, the marble is rolling off of a tabletop, falling 1 meter to the floor. It happens to land 3 meters away. The key to this problem is the motions in the x and the y directions are independent. So when we're asking about how long the marble is in the air, we need not worry about its vertical velocity, but just the horizontal velocity. And so for that, we can use the quadratic equation. Y is equal to negative 1/2 gt squared plus v initial in the y direction times time plus y initial. Now, what we're looking for is when y is equal to 0, that's when it hits the floor, so 0, negative 1/2 gt squared. It actually doesn't have any initial y velocity at all, because it's just falling off the table. The initial velocity is actually in the x direction, so that term goes away because VIY is 0. And the y initial is the height of the table, so that'll be yi. So what this shows is that yi is equal to 1/2 gt squared, or 2y initial over g, and we take the square root. That yields the time, which will be the square root of 2 times, what's the height of the table, is 1 meter, divided by approximately 10. I'm going to round for this problem, so the time is the square root of 2 over 10, or I can change that to the square root of 1 over 5. So 1 divided by 5, square root of 5 seconds. Let's break out the calculator now. 1 divided by square root of 5, and it's about 0.45 seconds. Okay. So t is a little shy of half of a second. Second part, what is the speed of the marble when it leaves the table's edge? So for part B, you have to ask yourself, if something is traveling for 0.45 seconds and it goes, what's the horizontal distance, 3 meters, then you can just use the definition of velocity, because the marble is not accelerating in the x direction, it's moving at a constant velocity in the x direction. And we know, we're being asked to find that velocity, but we know the distance. And so the velocity is just the distance in x divided by t. But we have the delta x and the delta t. The proper delta x in this case is 3 meters from the problem. And we know that the time is 0.45 seconds, so this is meters. 0.45 seconds in the denominator gives us 3 divided by 0.45, 6.67 meters per second for the velocity. A football player can kick a football such that it moves 15 meters per second. This involves the range formula. Let's go back to the memory bank. This is the range formula. V squared sine 2 theta divided by g. So if we're kicking at an angle theta naught with some velocity v0, we can predict the maximum range if we simply know the magnitude of the speed and then the g value. So the right angle in this case, the proper angle for maximum distance would be 45 degrees. 2 times 45 is 90 degrees, so the formula has sine 2 theta in it. So 2 times 45 is 90. Sine of 90 is 1. That's the highest sine ever gets. What's the largest range then? The range will be 15 squared times sine of 2 times 45 degrees, which happens to be 90. Sine of 90 is 1, divided by g. So if g is about 10, then we got 225 meters squared divided by about 10 meters per second squared. And there's one more, yeah, there, like that. So this is in the numerator, there's a velocity being squared there. So these cancel each other. 1 meters cancels one of the meters, and the final units are just meters. And we get about 22.5 meters, like that. How long will the ball be in the air is a different question. So the other formula for the time of flight is given in the memory bank, t time of flight. And so for that, we have 2 times the velocity and then it's just sine of theta divided by g. To maximize time of flight, theta should be 9 degrees. By kicking straight up, that would maximize the time of flight. Here, the time of flight's not being maximized. We have the sine of 45 degrees, so we have 2 times 15 meters per second. Sine of 45 degrees, which would maximize the range, is 1 over the square root of 2. And then multiplying by g, that's approximately 10 meters per second squared. So 1 of the seconds will cancel that. Seconds, the meters will cancel each other. The final units are seconds. 2 times 15 is 30 divided by 10. Again, 2 times 15 is 30 divided by 10 is 3. And so we have the square root of 3 over 2 seconds. How many seconds is that? Square root of 3 divided by 2, 0.86 seconds or so. I think I'm forgetting a factor of 2, though. No, I'm not. So 2 times 15 times sine, I'm in degrees mode, so 45. 2 times 15 times sine of 45 divided by 9.81, the more precise calculation. Right, okay. So about 2.1 seconds. So once again, that time could be larger if the angle were to change, but in this case, the football kicker is kicking for distance. So finally, we'll come back to the Unit 4 in a moment to deal with forces. Stand by. And welcome back to the study guide, final unit, dealing with forces and Newton's laws. A man pushes a pallet crate across the floor of the shop. He pushes to the right with a force of 100 newtons. There's some friction which resists with a force of 90 newtons to the left, and the mass of the crate is 60 kilograms. What is the acceleration? So we're going to need the net force, and that's 100 newtons to the right minus 90 newtons to the left. So the net force magnitude is just 10 newtons. We can make that a vector by saying that it's to the right. And then given the mass, we can find the acceleration. So for part A, the acceleration will be F divided by m. So 10 newtons divided by 60 kilograms. So our acceleration will be 1/6 meters per second squared, like this. And then what will the speed be of the crate after it has been pushed 3 meters, assuming it starts from rest? We're not told about time in that part, so we're looking for v final. We're being asked about speed. And so it's best to just use the version of the kinematic formula without time. Uh, it starts from rest means initial velocity equals 0. So like that. So v final is equal to 2a delta x. So it turns out that this works out to be 1 meter per second. And that is because we have 2 times 1/6 divided times 3, so we get 6/6 square root, and that's 1 meter per second. Finally, 2 tugboats are pushing a barge floating in a port. One tugboat pushes the barge north with a force of 3 times 100,000 newtons, and the other one pushes east with a force of 5 times 100,000 newtons. And then we're given the mass. So what's the net force on the barge? F net is equal to, let's say, 5i plus 3j times 10 to the 5th newtons. And then, and that will be the net force. You can write that a number of ways. I'm just indicating 3 and 5 are the vectors north and east, and then they're each times 100,000 newtons. And then that's the net force, and then in what direction? So we're looking for the the angle. If we're going 3 up and 5 across, what's the angle? We can find that with the tangent function. So tangent of theta will be equal to the y component divided by the x component. So theta turns out to be about 31 degrees here. You can get that by taking the inverse tangent of both sides. The inverse tangent of 3/5 is about 31 degrees. And then we're looking for the acceleration of the barge, but to do that we'll need the magnitude. So that's going to be the square root of 5 squared plus 3 squared. That's about the square root of 34, and it's really times 100,000 newtons. So F net is about root 34 times 100,000 newtons, and we have the mass. So if we divide F by m, we get A. So the square root of 34 times 10 to the 5th newtons divided by 6 times 10 to the 6th kilograms yields about 0.1 meters per second squared. So very slow acceleration. It's a very heavy barge. And to do that, we had to get the magnitude of the net force and divide by mass. So this has been a very quick overview of the study guide. Please don't hesitate to email me at jhansen2@whittier.edu with any further questions, and I wish you the best of luck. Thank you.